On October 22, 1707, 21 ships of the British Royal Navy entered the mouth of the English Channel in a thick mist. The navigator's charts indicated open water. Instead, 4 massive ships struck the Scilly Isles, and 2,000 men drowned in a matter of hours. The fleet was structurally sound, and the sailors executed their duties perfectly. The catastrophe occurred entirely because of a mathematical error. The navigators simply did not know their exact geographic position. Determining north or south positioning, latitude, was straightforward. By measuring the angle of the sun or the North Star relative to the horizon, a navigator could accurately place their ship on a horizontal plane. But finding longitude, how far a ship had drifted east or west, presented a temporal paradox. Because the Earth is in continuous rotation, tracing an exact longitudinal position requires calculating an exact difference in time. As shown in this 3D wireframe, for every hour of difference between a ship's local time and a fixed starting point like London, the vessel has traveled exactly 15 degrees of longitude. The prevailing scientific consensus assumed the answer lay in orbital mechanics. The brightest minds of the era promoted the lunar distance method, attempting to map a ship's position by observing the moon's relative distance to specific stars. This approach required hours of complex calculus and an absolutely steady hand. Operating delicate optical instruments like this brass sextant to measure minute celestial angles is impossible on a violently pitching wooden deck. Solving longitude was a localized engineering challenge. To measure geographic distance accurately, someone had to build a mechanical system capable of tracking time, completely isolated from the chaos of its environment. Standard 18th century timekeepers required absolute stability to function. They relied on uniform gravity and a completely stationary environment. The kinematics of these clocks depended heavily on sliding, metal-on-metal friction. Internal components continuously scraped against one another to regulate the release of energy into measurable intervals. To prevent that constant friction from physically grinding the machine to a halt, clockmakers applied chemical lubricants. At sea, the highly humid, salt-rich air quickly degrades the soil. The lubricant turns into a sticky, abrasive sludge, altering the physical resistance of the gears and destroying the clock's frequency. John Harrison, an English carpenter, theorized a completely different architecture. He determined that to survive a maritime voyage, a machine must operate entirely independent of chemical lubrication. Harrison built his first major prototype, known as H1. He engineered this massive array of anti-friction wells to eliminate sliding friction. Look at this animated diagram of a traditional Anger escapement to see the difference. As the pendulum swings, the metal teeth of the escape wheel physically slide along the surface of the anchor, resulting in a continuous loss of kinetic energy and high friction. This animation shows Harrison's replacement, the Grasshopper escapement. Instead of scraping, parallel arms execute a precise, stepping physical interaction. Watch the exact point of contact. The arms physically lift completely away from the gear, eliminating all sliding contact. By replacing sliding kinetics with this perfectly timed stepping release, Harrison built the world's first closed propulsion system, immune to maritime chemical degradation. The second physical variable threatening precision was the severe temperature volatility of global shipping routes. Under intense heat, metal microscopically expands and elongates. In standard clockwork, thermal expansion causes metal balance springs to physically lengthen when temperature rises. A longer spring takes more time to complete a single oscillation. This immediately slows down the clock's frequency, fatally skewing any longitude calculations. Rather than shielding the clock from thermal expansion, Harrison used the physics of expansion against itself. He designed the bimetallic strip, highly expandable brass perfectly bonded to steel. When heat increases, the brass expands faster, forcing the strip to curve. Harrison positioned this curve against the balance spring. As temperature rises, it physically clamps down, restricting the spring's length. He engineered an active thermodynamic feedback loop. The machine diagnosed its own structural distortions and mechanically corrected them in real time. Despite these breakthroughs, Harrison spent 19 years in developmental stagnation. His first 3 prototypes eventually plateaued in their maritime effectiveness. The primary flaw in these early machines was their massive physical weight, which generated massive inertia. An 18th century galleon is subject to extreme unpredictable pitch, violent sudden yaw, and punishing roll. This chaotic motion easily disrupted the heavy, slow-moving balance wheels. Achieving absolute stability against this macroscopic environmental motion required a drastic reduction in mass and a massive increase in mechanical speed. Harrison abandoned the sea chest appliance scale and introduced the H4 chronometer. He shifted the engineering to a high-density, pocket watch scale portable instrument. Inside this compact brass casing, he embedded a deeply complex, high-frequency oscillator, completely reimagining the fundamental relationship between physical size, speed, and environmental stability. The H4 maintained an aggressive, unyielding rhythm, ticking exactly 5 times every single second. This comparative vector diagram illustrates the physics of angular momentum. A slow-moving physical mass is easily knocked off its rotational axis by an external force, while a high-speed mass physically resists the exact same force. Inside the H4, the sheer kinetic velocity of the internal components was so high that it effectively overrode the macroscopic motion of the ship holding it. By generating true kinematic stiffness through sheer mechanical frequency, Harrison finalized his isolation matrix, conquering friction, heat, and motion. In 1761, the H4 underwent its ultimate trial. The Board of Longitude placed the chronometer on a ship bound for Jamaica, subjecting it to 81 days of intense maritime volatility and severe climate shifts. After mathematically traversing the Atlantic Ocean, the empirical data was clear. The machine had mechanically drifted by only 5 seconds. Across an 81-day transatlantic journey, a 5-second drift equated to a physical geographic error of roughly 1 nautical mile. This absolute, localized precision dismantled the scientific establishment's assumption that the solar system was the only viable reference point for geographic truth. Navigators now had the ability to map precise, repeatable shipping lanes. This exact geographic certainty rapidly accelerated global trade, empire logistics, and international commerce. This high-contrast visualization maps the direct technological lineage from Harrison's chronometer to modern global positioning. The intersection nodes on this modern GPS satellite grid are entirely calculations of extreme temporal precision. Our modern ability to perfectly map physical space is an exercise in mastering time. By isolating a precision instrument from the chaos of the natural world, a single carpenter mathematically mapped the ocean.